So I want to give an overview of what is to be on the last exam, okay, the final exam or the last exam, either way. So what have we covered? If we look at the textbook, we've covered Chapter 14, Turbo Machinery. We skipped compressible and open channel flow. This would be good for the aeros. This would be great for the civils, mechanicals. We'd rather do turbo machinery, something about pumps and fans and rotating equipment. External flow we spent quite a bit of time on. We skipped primarily all of 10, although there was a little section 10.6 where it covered boundary layer solutions and especially Blasius's, and we talked about the boundary layer thickness, and I'll cover that, as well as the skin friction coefficient for flow over a flat plate. So there's a little section 10.6 of chapter 10 that we skipped, but primarily the whole thing is skipped. Then differential analysis of fluid flow. That's the Navier-Stokes equations, the differential equations, get the right boundary conditions, and then solve it, typically for the velocity profile, somewhere. In a pipe, in a slot, somewhere, some simple geometry. Internal flow, now we talked about flow inside of pipes, real important for us. We talked about the friction factor, talked about a Moody diagram, talked about, well, the Reynolds number we introduced before, but laminar flow, where you had the friction factor is equal to 64 over the Reynolds number. Turbulent flow, you need that Moody diagram or some other correlation. There's a number of curve fits that people have put out there that are very good. Dimensional analysis. Because fluid mechanics doesn't have a lot of analytic solutions, you rely on experimental measurements and you extrapolate those. And so talked about C sub D, drag coefficient is a function of Reynolds number. How do you come up with the structure of why we're looking for only the drag coefficient as a function of Reynolds number? Well, you can justify it using dimensional analysis. It shows you, it leads to the grouping of parameters and the relationships. Momentum analysis we've had on previous exams, although it's important. Momentum analysis I'll just cover in this overview. Linear and angular momentum for a control volume. Real important for this class. Okay, as well as conservation of mass. We had Bernoulli's equation. You'll see I continue to say, okay, let's start with a modified Bernoulli equation. Let's go along the streamline from point A to point B, or point 1 to point 2. So Bernoulli's equation is very important. We continue to use it in pipe analysis, internal flow piping systems, as well as in turbo machinery. And Bernoulli's is a basic energy equation. Fluid kinematics. I know we've tested and we've covered the material, it's been a while, but what was that material derivative? And that very funny notation for cap D of T, of whatever, you know, that material acceleration, material derivative. So that was covered in the fluid kinematics, talking about vorticity, talking about divergence. Somewhere along the line, we had the general Navier-Stokes equation. Was that down? Did I already cover that? And differential analysis, the full Navier-Stokes equations. Fluid statics. You'll see you continue to go back to what a simple manometer is. You don't get away from manometers very far. It really is. We talk about pressure and air systems as inches of water column. That's referring to pressure measured by a manometer and how high that height is in a manometer. You may think, I've seen manometers. I know manometers. That's great. Master manometers, because it's really surprising how often we have to go back to manometers and think about it, especially when we talk about the pressure in air systems. And I find a lot of people get confused. It's like, you're talking about inches of water column? Yep, in a manometer to measure that pressure. Okay, a lot of things in statics, fluid forces on surfaces, whether they're planar, whether they're curved, how far they're submerged. We should be able to handle that. Talk about the center of pressure and also the centroid of an area that's submerged. Fluid properties, there was a whole bunch in there. One of the things that it's kind of interesting, we were introduced to the notion of the vapor pressure of a liquid. And we're even introduced in Chapter 2 to the idea of cavitation. And then we didn't really see it until way down here in Chapter 14, where it's a real practical problem or consideration in pumps. So cavitation was covered in Chapter 2. Cavitation was covered in Chapter 14. In 14, we talked about the net positive suction head. Net positive suction head to do what? Make sure that you avoid cavitation. Make sure that what you have available at the inlet to the pump is sufficiently high above what is minimally required to avoid cavitation in that pump. There's a lot of other fluid properties, viscosity, law of viscosity, density. I mean, there's surface tension was a fluid property, and introductory concepts. Well, there it is. Let's go chapter by chapter. So for turbo machinery, make sure we talk about a pump, centrifugal pump, a workhorse in mechanical systems, fluid systems. You have the I section, you have the impeller, you have the casing or the volute, where that it's really what the impeller does is impart high kinetic energy or high momentum, and then that is picked up and slowed down in the volute section and converted. It's like a diffuser. It's converted into higher pressure. Okay. We have pump performance curve, flow as a function of head, some curve like this. Cavitation, we just mentioned it, where you have pockets of vapor that form. And they form in low pressure regions, then their fluid is swept to a high pressure region, they collapse, and they can cause a lot of damage and loss of efficiency of machinery. The best efficiency point, it's really where you want to operate that pump most of the time. You put a system curve with the pump curve, and that's where you'll get the operating point, the intersection. The system curve has a characteristic quadratic shape to it. If it's a closed system, it goes through the system curve, goes through the origin, 0, 0 on the head versus capacity plot. If it is an open system, it can be shifted up or shifted down, depending if you're trying to pump uphill or up from a lower tank to a higher tank. This would be the shifting up of the system curve. Or if it's shifted down like that, that really is you could get rid of the pump and let it siphon. Just let the system flow from a higher tank to a lower tank. Okay. Operating point is that intersection. Net positive suction head required. What is, first of all, the net positive suction head? It's the static pressure at that point at the inlet to the suction of the pump plus the dynamic pressure minus the saturation pressure, the fluid vapor pressure. Sometimes I'll write Psat, sometimes I'll write PVAP, VAP, sometimes I'll write PV. It's all the same thing. It's the saturation pressure of the fluid at that temperature, which is being ingested into the pump. If it's warm fluid, you're going to have a harder job to stay away from or avoid cavitation, because typically when it's warmer, what's higher in this equation? When it's warmer, the saturation pressure. This is a function of temperature. Okay, what is another name for the sum of the static and the dynamic pressure? The what pressure is called the static plus dynamic. Here's a hint. What's that? The pitot tube, right? The pitot tube. What did the pitot tube measure? Fluid flow velocity, fluid velocity at a point typically. And how did they measure it? By introducing something into the flow like that. And what did they have at the tip of this probe that's introduced into the flow? What was at the tip of that? And you have to align it in the direction of the flow. Did I pass one around? Didn't I? Did you look at it? What was at the tip? A hole. What's the hole for? Let fluid flow through the hole? No. Basically, the fluid that's in that hole and down through the passageway is at rest. So what happens to the flowing fluid when it comes and it just comes right there? It comes to rest. What do we call that point? Stagnation. So the static pressure plus the dynamic pressure equals what pressure? Stagnation pressure. It's the stagnation, pressure stag. So another way to look at net positive suction head is it's the stagnation pressure minus the vapor pressure, saturation pressure, and different names for that pressure, but we know what we're talking about. Let's call it the vapor pressure of the fluid. Okay, so how do you calculate what's required? Well, the pump manufacturer gives that to you typically. You look on the pump specs. They say we need this much head, otherwise you're going to have trouble with cavitation. And then how do you calculate the net positive suction head available? Well, you do an analysis looking at where's the fluid coming from, what's the pressure over here, maybe you account for some losses in the piping system to get there. Have you solved the problem requiring you to make that calculation yet? We'll have an opportunity to solve one today, but you should be able to solve that. Okay. To calculate the net positive suction head available is simply just typically a lot of work. Just have to work on it. Okay. Affinity laws. Real important. If I had to say something would be on the FE exam. Are you going to take the FE exam? You're going to pass the FE exam? What percent of the FE exam is fluids? A good chunk. Think about it. You have let's say 100 and almost 30 semester credit hours to get a degree, BS in mechanical engineering. How many hours are really devoted to fluid mechanics? 3. You could do the ratio. 3 out of 130, that's over 2%, but under 3%. But what percent of the FE exam is fluid mechanics? Over 10. So, in the grand scheme of things, maybe that psychology class is not going to help you pass the FE exam, but this class will. And you want to. You want to. Did I mention in strong encouragement that you need to take that exam? Did I encourage you to? Some people are like, well, I don't really care about it, whatever. No, no, no. Look at the trend in society and everything else. You have to be licensed to do anything. You have to be credentialed to do anything. Okay? So get that certification, just like you're going to get a degree in Bachelor of Science in Mechanical Engineering from an ABET accredited program. You want the FE so that you can become a PE. You say, well, it's not all that important. Wait till you're 50, 55, 60 years old and you still want to be employed. What year will it be when you're 60 years old? You don't want to know, huh? That's too far out there, right? You want that. You may say it's not needed in 2016 or 20 whatever it is, but it will be needed more and more. All right. And I'm amazed so many students will not take that exam. I think they have a fear of it. Well, study a little bit and you should pass it, really, honestly. You should pass it. Okay. Does anybody know if anybody that personally passed it? Do you have any friends that took it and passed? 1, 2, 3, 4. Is that it? Well, hopefully. Did they encourage you to take it? Yeah. Yeah. I had a TA that worked with me, Emmanuel. I don't know if you knew Emmanuel. He graduated. He studied. I'm sure if he looked at his raw score, it was, through the roof. It was high because he was so well prepared. You don't need to be that well prepared. You just need to pass. Okay? He did a great job. I know because I watched him study. Anyway, I bet you will see something about the affinity laws on it. So, it's not often that you change the diameter of the impeller, and it's not often that you change the fluid density. And if you do, go back and review the affinity laws that account for the change in diameter and the change in density. We covered them. But what will you change typically? The speed of the pump. The speed of the pump. It's so the volumetric flow rate, the head, and the brake horsepower. How do they vary as a function of the speed of the pump? And the volumetric flow rate is proportional to the speed of the pump. Let's use N for the speed of the pump. The head is proportional to speed of the pump squared. And the brake horsepower is proportional to the speed of the pump cubed. If you can remember that, you can solve a lot of affinity law problems on pumps and scaling. Okay? All right. We covered a lot of centrifugal pumps, centrifugal pumps, centrifugal pumps, centrifugal pump. But there are a number of pumps that are called positive displacement pumps. Maybe if you worked in an engine, the oil pump in an automobile engine or diesel engine typically is a positive displacement pump. It ingests and then squeezes out a certain volume of fluid at a certain rate. In the medical profession, positive displacement pumps are used to provide flow rates of medicines to patients in hospitals. So there's still a lot of positive displacement pumps. But we just noted that they have a particular characteristic that you want this flow rate, they'll work really hard to give that flow rate, no matter if they have to provide this head, this head, this head, this head, this head, this head, or whatever head. And so they're very steep. Yeah, they have a little slight backward curve to it, and then they break because it's too much. But basically, it's a constant volume flow rate application is a great positive displacement pump. There it is. That's that chapter. Did I miss anything? Let's solve some problems, maybe. But before we do that, let's go take a look. We skipped these two chapters. Chapter 11, external flow, real important. So we had the concepts of lift and drag. What was the direction of the lift and the direction of the drag? Was it related to the primary dimension of the object that's in the fluid flow? Here's the fluid flow. Maybe we had an object and it had this axis, right? Is the lift and drag related to the axis of the object? No. Lift and drag are related to the direction of the flow field. Okay. Then we had C sub L and C sub D. Professor, I can't remember what those are. Oh, come on. Come on, come on, come on. You don't need an equation sheet for everything. You need an equation sheet for your name? No, come on. What is the equation for the lift coefficient? Well, you're going to cast in dimensionless terms the lift force. Right? And often these things are related to the 1/2 rho v squared. What's 1/2 rho v squared? Dynamic pressure of the fluid flow. And we need to make this dimensionless, so we have to put an area. So you can either think of multiplying the dynamic pressure times the area to get a force, or you just put F of L divided by A, put it up there. Either way, whatever your thought process is to make it work. But what type of area do you want? Well, if this object is primarily designed for lift, you use what they call the planform area, right? Looking down on the surface. If it's not designed for lift, then you would use the silhouette area looking at it from the direction of the flow. Most of the time, silhouette area, unless it's designed for lift. So you want to use the same area in both of these equations for the same object. So if it is designed for lift, you will use the same area here. Even though that may seem a little oxymoron, it may not seem like that's the most logical area, but it is. Otherwise, if it's not designed for lift, if it's just having to suffer drag, then it's the silhouette area. Bluff body, what does that mean? Well, it's opposite of streamlined body. What is a streamlined body? Typically, you have to get some width through it, but on the back side, there's some shape to help it avoid separation. Why avoid separation? Because there's two components to the drag force. What are the two components to this drag force right here? We have the viscous and the pressure or form drag, they call it. What do you mean by a large pressure form drag? Why is that? Well, it's a low pressure region and a high pressure region that gives you a high form drag or pressure. True? And how do you get such a low? You get a wake region. You get in that wake region, because of separation, you get a low pressure. And so you want to avoid that. So you want to delay or avoid the separation, the large wake, make it really small. It reduces not the viscous, it reduces the form drag. Okay, so bluff bodies, typically you don't have the option of streamlining, or it's not streamlined, and you have a large wake region. Okay, let's say I have a tall building, and usually buildings are something like rectangular, and you have flow, it's a, 80-story tall building. You have airflow around it. Well, it's a very bluff body. It's not streamlined at all. And so the aerodynamic load on the structure like that is going to be given by a lot of separation going around the edges and backside. Okay. I just mentioned a lot about separation, but what exactly is separation? Yeah, it's really good to understand the flow that goes around the cylinder. That's the easy one. So as we're going around the cylinder, if you think of this section of the flow, that quadrant of the flow, what's happening to the velocity as you're going from point, let's say, A to point B? What's happening to the speed of the flow? It's going faster and faster, isn't it? So it's accelerating. What about the pressure from point A to B going around the cylinder? This is flow, and what happens to the pressure going from A to B? It's decreasing, it's going down. That's what they call, what type of, either an adverse or favorable pressure gradient. It's favorable, because what's happening is you're going and decreasing pressure and it's accelerating. That makes sense. Okay? But then you come around on the back side in this quadrant, and what's happening to the pressure? Well, it's trying to increase. And what about the speed? Going down. That's an adverse pressure gradient. You're going into a higher region of pressure. It doesn't like it. It can do it. It's called a diffuser, but it's challenging. Okay, so what happens is out in this region further away, the velocity profile, if you just think of a velocity profile like this, is strong enough, but near going close to the surface, the velocity profile, the speed just a little bit away from the solid surface, the cylinder surface, is not fast. And there's not a lot of dynamic pressure at the expense of the speed to recover the static pressure. Hence, you get such a severe adverse pressure gradient that you get reverse flow. At that point that you start to get reverse flow, that's the separation point, and then you develop a wake. That's this point of separation. It's really good not just to listen to me talk through it, but that you master that concept, because I really think that will carry you a long way to understanding the behavior of fluids. So we have when you have a bluff body, when you have a lot of separation, the wake regions there, you can get what they call Reynolds number independence for the drag coefficient. I know that when I took fluids, it's like, why do they only quote one number for C sub D? I learned that C sub D is a function of Reynolds number. But after a while, that C sub D settles down and goes flat as a function of Reynolds number. And in this region, it's independent of the Reynolds number. It's just a single drag coefficient. And a lot of fluid applications, they're out there that Reynolds number independent region. What's a classic example? Just look at automobiles. You can look at a Wikipedia page. I don't know if I showed it to you or encourage you to look at. You can look at the drag coefficient for automobiles going back to, different pickup trucks and different cars over the many years. And you can see how the manufacturers work to streamline them to reduce the drag coefficient. But they only quote one number. Because when you're running down the road 60, 70 miles an hour, my daughter just drove down from Austin. She said, Dad, if I wasn't going 80, it was dangerous for me. I needed to go 80. The people were just blowing past me, Anyway, you may go even faster than 70 miles an hour every now and then on the road. But out in that speed, it's a constant value for the drag coefficient works. That's why you'll see drag coefficients quoted with a single number for a lot of applications. All right, so that's automobile vehicles. Superposition principle. Well, if you have this part and that part and this part, you can get the total drag by thinking of different components and adding up the flow field over it and the resultant drag force. Flow over cylinders and spheres. This whole thing that I just was talking about right here is very, very important. Laminar, when it goes over slowly, and then you have a recirculation region as the flow starts to speed up, the approach velocity goes faster, the Reynolds number is faster. You get the vortices that are shedding, they periodically shed. There's what they call a vortex street, little vortices leaving. You have a large wake region when you have that defined separation point. And then if you get turbulent boundary layer before it hits that separation point, it can actually navigate the turn in the adverse pressure gradient region. It can delay the separation. It can reduce or make the wake region smaller, and it can reduce the net form drag on the object. And so that's when you will come out with a C sub D as a function of Reynolds number. It'll come down and get a little flat, and then it'll actually drop like that. And that's what's happening. And in some balls, in games, like golf balls, they purposefully treat the surface of the golf ball such that when in flight, you are sitting in this region, and the golf ball goes further. But then in some balls, table tennis, that's right. What do you call that? Ping pong? Do they dimple the ping pong ball? Unfortunately, because it's just not out there at that high Reynolds number. You're hitting it, it's flying, but as I understand it, it's not that fast. Okay. Maybe the Chinese would prove me wrong, huh? Aren't they the champs of that game? Okay, anyway. So golf balls have rough surfaces. And then the last was the Magnus Effect. So if you have a rotating sphere, and as I understand it, when you're hitting a golf ball, let's say you're hitting it this direction, the trajectory is that way. If the golf ball is spinning with the backspin like this, right, into the flow, it gets a particular increased lift, but then when after it slows down, it'll actually drop pretty sharply. And when it drops, it's better if you want it to stay in the region where it first hits the ground to come down at a steep angle than at a shallow angle. Shallow angle, you're going to bounce and keep going. Steep angle, it'll just fall, land, and lay there on the green. True? Who's a golfer? Only a few people? Do you know how to hit with a backspin? No? Have you seen some people really do it well?
If I do it, it's not on purpose.
It's not on purpose? Honesty. But I think I've seen it where in some tournaments where the real professionals hit it, it's like, how did that ball just pop on the green and just stay there? You know? Backspin and aerodynamics, plus also when it hits, there's a help on keeping it from popping and going out. All right, well, I'm not a golfer. Actually, I have a tendency to be addictive to things, and so I was fearful of being addicted to golf, and so I just never played. Seriously, I was afraid if I went out and started playing, I'd be like, oh, I got to play. And I worked with a guy. He would come in at 8 o'clock in the morning. I had 9 holes in this morning. It's like on a Tuesday, and then Wednesday. I had 12 holes in. You know, it's like, this guy's playing before work, after work, every day on the weekends. And anyway, he was very much into golfing. Now, this is out of chapter 10. Only thing that we really covered is at section 10.6 in the discussion of boundary layers. I even tried to cover up some of the results. To focus on, we want to talk about the growth of that boundary layer thickness. I think that's an important concept to have for flow over a flat plate. In the laminar region, Blasius, over 100 years ago, gave us this solution. And in the turbulent region, you can get how it grows as a function of Reynolds number, and it's experimentally confirmed. And then the other is the friction coefficient. Once I have the velocity profile, I can take the derivative of the velocity profile at the surface, du dy, evaluated at the surface, y equal to 0, multiplied by viscosity, and isn't that the shear stress? So the wall shear stress. And you can get the local law shear stress, meaning I'm going to start my knife edge sharp plate, and I can get it at this location, this location, this location, this location, that location. It's going to be coming down. It's not a straight line, but it's coming down as I'm going further away from the leading edge measuring x. You also get one experimentally in the turbulent region. So it goes down, then it kicks up, and whoops, that's a bad rendition. Then kicks back down again for the local cease of f of x. Now, in chapter 11, for external flow, they revisit it and they give the average friction coefficient. All you did was integrate the local from 0 to the L or 0 to X and to divide by that distance. And you'll see the parallel. See the parallel between the two equations? Over the square root of the Reynolds number. But this time it's measured at L or wherever you're going to measure it. It's average from 0 to L. Okay. And then 0.664 multiplied by 2 is 1.33. Likewise, you can do the math and get the average for the turbulent. And so these table 10.4 in chapter 10 and these equations in chapter 11 tie in very nicely. Okay? That help? All right, continue on. Chapter 9, well, we talked about the differential analysis of fluid flow. Get the Navier-Stokes equations, now do something with them, solve them. Go back to engineering analysis 1, engineering analysis 2. Okay, so we reviewed scalar fields, vector fields, divergence, gradient, curl, Laplacian. What's the Laplacian? Del squared. The divergence theorem, del dot, with the divergence, and then the theorem, sometimes Gauss's divergence theorem. It helped convert an area integral into a volume integral. Continuity equation, conservation of mass. The stream function, such that it guarantees the solution of the continuity equation. Cauchy's equation, but then we introduce it for Newtonian fluids, so we get the Navier-Stokes equation. We can solve problems in Cartesian coordinates, cylindrical coordinates. Rarely have I ever seen much in spherical coordinates, but those two coordinate systems, Cartesian and cylindrical, are the ones that you need to, that's the problems that are solved in our textbook in those coordinate systems. The key, once you have the differential equation, is get the right boundary conditions and then be rigorous with the math. Separate, integrate. Typically that's a good strategy. And come up with a velocity profile analytically. There's not many cases. So learn those cases and you'll do well. So you have u as a function of y, maybe going out this way. Here's y and here's u. Or u as a function of r, maybe I have a center line and I have a pipe and I'm thinking as a function of r, and I have u as a function of r. Okay. Internal flow. Idea, we've really emphasized laminar flow, internal into a pipe. If it's fully developed, what is the shape? Quadratic shape to it. Nice bullet shape or quadratic shape to it. Here again, I know that the Reynolds number was introduced in either chapter 1 or chapter 2. It really is a relationship between the inertial and the viscous forces that compete to either keep the flow well organized and fluids stay in their lamina or layers, or disorganized where it's a lot of mixing, it's turbulent flow. Critical Reynolds number to separate the laminar from turbulent regions, 2300 for flow in a pipe. And when you have turbulent flow, again, think of that fluid in a lamina and it starts to mix and go all over. Entry region. These are pretty easy to remember. It's 10 diameters. So if I have an entrance into a pipe, go down 10 diameters, and if it's going to be turbulent flow, it's well mixed by 10 diameters. Okay. If it's going to be laminar flow, then it's 120 the Reynolds number times that many diameters. Okay. Hydraulic diameter, so if you don't have a round, you can use the equations, treating it if it's round as if it had a equivalent hydraulic diameter for cross-sectional area over the wetted perimeter. The friction factor, function of Reynolds number and relative roughness. This is the dimensionless pressure drop, isn't it? The friction factor. And that was the y-axis in the Moody diagram. The x-axis was the Reynolds number. Did I say that every now and then I will ask a question on an exam and I'll give students a blank sheet of paper and I'll say from memory, no equation sheet, no notes, nothing. Reproduce the Moody diagram with as much detail and as to scale and as accurate as possible. Did I encourage that? Well, I'm going to pass out a Moody diagram because it's really important. You don't want to pass a class like this and somebody say, hey, look at this chart. Wow, that's a neat chart. I've never seen something. No, you don't want to do that. It's like passing dynamics. F equal ma, what's that? Never heard of F equal ma. Okay, so in this chart, it has a laminar region, has a transition to turbulent, and the bottom curve in the turbulent region is completely smooth. But then you have different roughnesses, increasing roughness. And you get out into this region in here, and all the curves will eventually get to a flat. And that's where it's the friction factor is independent of the Reynolds number. Just like we had for external flow, you have Reynolds number independent drag coefficients. Here you have Reynolds number independent friction factors when it's flat. Okay. Usually there's a line like that separates it. And they give it a funny name like complete turbulence or fully turbulent regime. It's Reynolds number independent area or regime. We do spend a lot of time in applications where it's turbulent flow, but not so extremely turbulent, and the pipes are relatively smooth, why have a lot of rough pipes? Why? I mean, you eventually have rough pipes due to junk depositing on the walls in them, but in a brand new pipe system, we don't purpose to put in rough pipes to increase the pressure drop. And a lot of copper tubing, very smooth. BC, very smooth. Steels, you know, cast iron, that would be the roughest. Okay. Mechanical engineers don't put in a lot of cement pipes. Civils do, right? But there you go. So a lot of applications in this. Somebody says, give me a friction factor. Give me a numeric number for a friction factor. For turbulent flow, for smooth pipes, and it's not too fast, but it's not too slow, that it's laminar, give me a friction factor number. What number are you going to give them? That's why it's good to memorize this chart. Are you going to give them a friction factor that's 5? Ridiculous. That's way off. No way. How about friction factor of 0.5? Ridiculous. Way too high. Okay. Friction factor of 0.05. Okay, now you're getting down there in a reasonable range. Friction factor of 0.02. Sure, there's a lot of problems. 0.02, 0.03, 0.04. How about friction factor of 0.002? No, it's too low. So you should know that these values, especially around in there, 0.03, 0.05, 0.05 is a little high actually, but you can almost guess one, because if you have to solve some problems, often you have to iterate numerically, and then if you're iterating with the Moody diagram, it's a real challenge. You don't know the fluid flow, speed, hence I don't know the Reynolds number, hence I don't know the friction factor. Well, probably best to guess a friction factor and then start the cycle of iteration that way. Okay. I know I tried to emphasize that earlier in this semester. Do you remember me trying to emphasize that? Okay, good. Because I remember being a student, I can remember where I stumbled, thinking, what is going on? How am I going to? I don't know what Reynolds number it should be. I don't know what velocity it should be. But often, if you can get in the ballpark for the friction factor, you can start that iteration process. Okay. The whole idea of laminar region, turbulent, fully turbulent region. This is the basic equation for the head losses. You get that FL over D coefficient for the major, and then you have just the K for the minor, and they both multiply something like 1/2 rho V squared if you're talking about pressure loss, or 1/2 V squared if you're talking about energy loss per unit mass of flow, or 1/2 V squared over G if you're talking about head loss. Did I beat that into your mind already? Those three forms, 1/2 rho V squared, 1/2 V squared, and 1/2 V squared over G. And I think if you get that down, it'll save you a lot of units problems as you go and solve problems. Okay, but you multiply that times whatever. This is your dynamic pressure or velocity pressure, or it's your dynamic head, whatever term you want to give it. That 1/2 V squared over G, I would call that my dynamic head. Okay. Equivalent length, well, you can just compare these two, and you say, I'm going to take this loss coefficient and make it like an equivalent length for the same friction factor diameter of my piping system, and so L equivalent would be the loss coefficient times diameter divided by the friction factor. And now I can think of, oh, that fitting added 3 extra feet of piping, or it added 20 extra feet of ducting, something like that. Helps with the comparison of components. Modified Bernoulli. So our raw Bernoulli equation, running out of room, is pressure plus 1/2 rho V squared plus rho GZ. That's all at, let's say, some inlet point is equal to the pressure plus 1/2 rho V squared plus, I got to get rid of this, plus rho GZ, all at an exit point, 2 points on a streamline, steady flow. And you can add in here some pressure gain. That would be modifying your Bernoulli equation with the pressure gain. Where would the pressure gain come from? Go through a pump. The pump added. Or you could have a pressure loss. What are your pressure losses due to? Major and minor. And then you could also have a pressure loss from, let's say, a extraction of a turbine. There was a pressure drop across the turbine. The turbine's purpose is to extract flow energy out of that fluid stream and produce work. Okay, so that's the modified. We talked about the kinetic energy correction factor. Was that symbol beta or alpha? What was the symbol even for the kinetic energy correction factor? Alpha. And that alpha goes right in this term right here, alpha. And right in that term right there. And it was a little bit where you're using the average velocity, and you have a velocity profile, and each little chunk of fluid has its own kinetic energy. Luckily, what is alpha often equal to? Close enough to 1, a little over 1. Okay. Piping networks, so you could have series and parallel pipes with fittings going in there. You just have to be cautious and tedious and set up the equations and solve the problems. And we didn't really cover, I wish there was more time to talk about flow meters. They're very important. And some flow meters just introduce an obstruction into the flow, and then they measure the pressure drop across that obstruction, and then they have a very good correlation to tell you what the flow rate is. So anyway, that's that chapter. At this point, this is the last chapter that's kind of new. We haven't been tested over. It's dimensional analysis. So the concept of dimensions, what would be a dimension? Length, mass, time, temperature, and then some others, but those 4 will do us well in this class. Units, SI, so we have the length, the meter, mass, a kilogram, a time, a second, temperature, Kelvin. You could do USCS, although we don't use it. We use it on the streets and in business, but we don't typically emphasize it when we do dimensional analysis in a class like this. We can do pretty much everything in SI units. So we cast equations in dimensionless form. You have the Buckingham pi theorem. So you look for pi groups. They're groups of dimensionless parameters, or the groups are dimensionless. Okay. We look for the empirical correlations, meaning experimental data fitted the correlation or flushed it out. A lot of times dimensional analysis say this group is related to that group, but we don't know exactly how. You have to go make some measurements to fit the coefficients in there. There's some common parameters. What's MA? Mach. What is it defined as? Ratio of? Speed to the speed of something of the fluid. What speed? Speed of sound. What is Reynolds number? Inertial to viscous. What is C sub L? Lift coefficient, lift force, cast in dimensionless form. You divide it by the dynamic pressure area, and then the drag coefficient, and then the friction factor. So these are the pressure loss. This is the force drag. This is the force lift, inertial to viscous, and this is the speed to the speed of sound, V over C. I think use C for the speed of sound in the object. And then Reynolds number independence for bluff bodies. That's a major theme. It's been emphasized in a few chapters already, hasn't it? Well, the rest of this we've covered. So in the interest of time, I'm not going to go through it unless you request that I go through it. I have some problems I can solve. Let's solve some problems. So for flow over a smooth flat plate, the transition from laminar to turbulent flow occurs when the Reynolds number is about what numeric value? D. True? 500,000. What will some students give me as a next answer? The most popular second answer, which is incorrect. Which will they give me? They'll give me around this one, which is close to 2,300. And for over a flat plate, it's 500,000. For a car moving on a flat road, so this is our car, flat road, at a high rate of speed, let's say you're going at 60 miles per hour. The power developed by the engine to overcome aerodynamic drag is? So you're thinking about the W dot of the engine. The engine is running and it's producing some power. The power is getting through the drivetrain to propel the vehicle down the road at a constant speed. If you shut that engine off, it would slowly coast and come to rest. True? But if you're running that engine, it's providing power to overcome that frictional aerodynamic drag. Okay? So the question is the power developed by the engine independent of the vehicle's speed, inversely proportional to the vehicle speed, proportional to the vehicle speed, proportional to vehicle speed squared, or proportional to the vehicle speed cubed? I'm going to give you a minute. I'm going to pause. Okay, so let me pick this up. A lot of people did know how to solve this problem. They're saying, you know what? The power to overcome the aerodynamic drag, W dot the drag aerodynamic is, the aerodynamic drag is going to be the drag force times the vehicle speed. And they look at that and they say, aha, proportional to the vehicle speed, they want to answer C. But the drag force on an automobile, we would consider that either a streamlined body or a bluff body traveling at this speed. B-L-U-F-F, bluff body. What do we know then? That the drag coefficient is not a function of the Reynolds number. Hey, it's not a function of the Reynolds number was rho v, some length scale divided by me. Hey, it's not a function of v, right? But what is f of d? F of d is equal to, unraveling, the drag coefficient times 1/2 times some area. Oh, look at that right there. So yes, this is a constant, but f of d is proportional to v squared. Hence, you get this very funny relationship that it's, I could write it out, c sub d 1/2 rho v squared area times v. So what do you pick up? Is proportional to for external flow over a streamlined body, which statement is true? I'm going to pause and come around. So external flow over a streamlined body. Well, when they see streamlined body, you think of, and they're going to talk about the drag, right? The drag. The friction drag is what dominates the drag on a streamlined body, if it's well streamlined, true? Okay, so the friction drag is proportional to, let's say, the shear stress at the surface times some area, some average shear stress at the surface times some area. And this average shear stress at the surface, thinking of somebody's viscosity law, mu du dy at the surface, y equal to 0 times some area. So I know this is some average, okay, but it's proportional to viscosity. It's a strong function of viscosity. And if viscosity goes up, what does the drag force do? Goes up. So a lot of times you look at this two parts and you consider each part independently. So the friction drag is a strong function of viscosity. So we're going to get rid of the weak function of viscosity. So that's all gone. So B and D are gone. Then we look at the second part of the question. Increases with increasing viscosity. So if the viscosity goes up, what does the friction drag do? Goes up. So that's okay. And then right over here, decreases with increasing. No, that's no good. No. Best answer, A. What is the purpose of dimpling on golf balls? Decrease the air pressure on the back side of the ball, decrease the air pressure on the front side of the ball, increase the air pressure on the back side of the ball, increase the air pressure on the front side of the ball, or increase the air pressure on the sides of the ball. Okay, so we talked about the golf ball. And a lot of the drag, let's say this is the direction of the drag force because the air is going that way on the golf ball, was because you had a high pressure here and a low pressure there. The dimpling is going to do what to the drag? Reduce the drag force. How would it reduce the drag force? You could either reduce the high pressure in the front or increase the low pressure in the back. Wouldn't that do it? But it seems funny that you're increasing the low pressure in the back. But that's what you're doing. True? Okay. So the best answer would be increasing the air pressure on the backside. If you decrease the pressure, it would make it worse on the backside. True? Yeah. The phenomenon of producing lift by the rotation of a solid body, especially a sphere, is called the Magnus Effect. We covered that one already, right? Water pump delivers 2.1 cubic meters per minute at 45 meter head. So here is my pump. They give me Q is the flow rate through, 1.2 meters cubed per minute. And what do you mean by 45 meter head? What is that? Yeah, so basically from this point to that point, the head 2 minus the head 1 is 45 meters. There's an increase of the head, energy per unit weight of the flowing fluid. The outlet has 45 meter higher head than the inlet. The pump efficiency, so you're supplying some shaft here, and the efficiency of the pump is 70%. What is the shaft power, W dot shaft, needed to run the pump? And you'll need a calculator. All right, so how do we solve this problem? I would encourage you to remember the head is energy per unit weight. True? And so if you just want to think about units, a lot of times that'll help. I'm looking for power. There's going to be a difference between the shaft power and the fluid power. So I'm going to talk about the shaft power is equal to the fluid power, right? But only 70% of the shaft power gets into the fluid, so I'll divide by the efficiency of the pump. Because I'm looking to calculate the shaft power. Okay, well, what is this fluid power? Well, the fluid power would be the energy per unit time that's getting into the fluid. But the energy per unit time, I have energy per unit weight times weight per unit time. That'll work. But sometimes I think about mass per unit time or volume per unit time. Either way, I would just have to have the volume and then the weight. So depending on how your mind works, you don't need to memorize the equation. You just say, oh, I have 1 over the efficiency times energy per unit weight, weight per unit volume, volume per unit time. That'll give me my power. Okay, so let's work it out. So this is W dot shaft is equal to 1 over the efficiency. Energy per unit weight, that's the H2 minus H1. That's the change in the head. In meters, it's 45 meters is the number I'm going to substitute in there. Then I have the weight per unit volume. This one may be a little challenging. So what is the weight of water per unit volume? Let's say I had a volume of 1 cubic meter. How much mass is in 1 cubic meter volume of water? 1,000 kilograms. How much weight does 1,000 kilograms of water have? Multiplied by G, 9.81. So what is rho times G? Gamma. Rho times G is gamma. This was the weight per, here, this is the mass per unit volume. Isn't that the density? And G, I know you think of acceleration, but it's the weight per unit mass. It cancels that. And so when I put gamma, it's the weight per unit volume. That's what I need right there. As I need gamma. I need rho G. And then for the volume per unit time, well, that's Q. Your mind may work different than mine. And I'm trying to re-establish something that we did a long time ago in this class. But we have 1 over 0.7 times 45 meters. Now, rho G. You solved a couple problems before. Everybody remembers rho of water is 1,000 kilograms per meter cubed. But what is gamma of water? 9,810 newtons per meter cubed, or 9.81 kilonewton per meter cubed, whatever you like. So 9.81 kilonewton per meter cubed. Did I do gamma right? I like SI units, but I also like USCS units. What is the density in USCS units for water? 62.4 pound mass per cubic foot. What is gamma for water? 62.4 pound force per cubic foot. Actually, I think a lot of fluid problems are easier to work in the United States customary system of units of foots and pounds. I really do. But anyway, let's continue on. We have gamma, which is rho G. And then we have a volumetric flow rate was 1.2 meters cubed. Get rid of that minute, 60 seconds. And let's think about units. We're going to do the meter cubed, get rid of that. We have a kilonewton times a meter. Well, just get rid of the kilo on there. The newton times a meter is a joule. And a joule times a second is a watt. And what did that come in at? 12.6 kilowatts, which is B. All right. Fluid with vapor pressure of 4 Pascal. So PV is 4 Pascal. And a specific gravity of 13. What do you mean specific gravity of 13. What symbol do I use? Do I use gamma is equal to 13? What are the units on this specific gravity? Is this right? Is this the right symbol? No. What is our, that was specific weight, or weight density as I like to call it, that gamma. But what is the specific gravity? S of G. S of G is our symbol for specific gravity, and its numeric value is 13. What are the units? What are the units on this specific gravity? It is actually dimensionless. What is it defined as? Density of the substance of interest divided by the benchmark density, which is water, 4 degrees C, 1,000 kilograms per meter cubed. So it's water, if you want to be precise, 4 degrees C. Okay. It's used in a barometer. If the fluid column height is 0.84 meters, what is the atmospheric pressure? Well, I've got this tricky thing called a barometer. I have to, in my mind, I'm thinking I have a little pan of this fluid, and then I have this inverted test tube in the fluid, and then I have the fluid height up here, and this height they just gave it to me is 0.84 meters. And what's above this in this region right in here? It's essentially a vacuum, or it's equal to the vapor pressure of the fluid. So it's the pressure is equal to PV, which is 4 Pascal. Okay? So what is the atmospheric pressure in kilopascal? Well, what do we do with the barometer? We say that this pressure right here is equal to that pressure, is equal to that pressure, is equal to that pressure, that pressure, that pressure, that pressure. Why? Because the fluid in the container is all at equilibrium. It's just sitting there. It's not motion. There's no motion to it, right? And so at every layer of constant elevation, it has the same pressure. At every layer right here, it has the same pressure. At every layer there, it has the same pressure. So at every layer along the top surface, same pressure. And I go inside the test tube, and it's the same pressure. So I extract a FBD. What do you mean by FBD? FBD. What do I extract? Free body diagram. What's beating down on the top? The vapor pressure. What's beating up on the bottom? Atmospheric pressure. Okay? I'm going to do one-dimensional. Sum of the forces in the X must equal to 0. What goes right here in my free body diagram? W. What is that? The weight at the center. Okay, so what is my weight? It'll be the rho of the fluid, G times that H, times, let me do this. Let's do this. Rho G volume. How's that? Or maybe you like to do the mass and then times G, but the rho G H times the area is, I'm just going to leave it area. Okay? Okay. So we have the pressure acting along the top area. We have the pressure acting along the bottom area. We convert those to a single force, so we're going to have PV times area acting down plus the weight, which is rho GH area acting down, equal to the pressure atmosphere times the area acting up. Did I do the 2 down equal to the up? On my free body diagram, sum of the forces in the Y, cancel the areas. And so my atmospheric pressure is equal to the vapor pressure plus, let's do rho of the, let me do specific gravity, rho of water, GH. Okay, so we're going to have 4 Pascal, that's easy, plus the specific gravity, 13, density of water, 1,000 kilogram per meter cubed, G, again, G, you can think of two things, 9.81 meters per second squared or 9.81 newtons per kilogram. Is that true? Yeah, so let's put 9.81 newtons per kilogram. I could have put rho G and put gamma there, but I didn't. Sorry about that. A little faster. And then what do we have? 0.84 meters. Okay, so kilograms go. The Newton per meter squared is a Pascal. You're going to be left with 4 plus right? And so this is 107 kilopascal. Makes sense? Okay, let's move on. Okay, oh man, I don't have enough time to solve all these problems. Water at 30 kilopascal and 60 degrees C enters a pump in a 25 centimeter diameter pipe at a flow rate of 0.15 meter cube per second. Calculate the net positive suction head available. Do you like that acronym, NPSHA? Yeah, that looks good. The net positive suction head available. At the pump inlet, for water at 60 degrees C, the saturation pressure is given. The density of the liquid is given. The viscosity of the liquid is given. And we're looking for an answer in units of meter for our net positive suction head available. So we want to calculate the net positive suction head available. Well, you guys have to remember what that is. What is it? It's our head. I'm going to use lowercase h for head, and it's called stagnation head minus the head vapor. All right. Well, what is my head stagnation? That's the head static plus the head dynamic. It's a static pressure plus a dynamic pressure, but we're talking about it in units of meters, which is head instead of pressure. And then we're going to have this, which is a minus H vap. Professor, I don't see that equation on my equation sheet. Well, I can't have every. I got a question yesterday on Thermo 1. Like, I'm having a hard time with all these entropy equations. Can you tell me which ones are important so I can ignore the rest? It's like, can't do it. Every equation I put on the equation sheet's there for a purpose, you know. It's like, so anyway. So let's talk about this in terms of pressure. The static pressure plus the dynamic pressure minus the saturation pressure, or the vapor pressure. And what do I do to get it in terms of head? I multiply this by something to get it in terms of head. Do I multiply by rho G? Or divide by rho G? If I divide that by rho G, do I get that? That's the right equation, isn't it? Sure. And so you could say that this rho G of water, they give you the density of water, but look, we're going to be close enough if we just round that off to 1,000. Will be 9.81 kilonewton per meter cubed. Or, I know that you don't like all these units, but 9.81 kilopascal per meter. Isn't that the same? Is that the same? So anyway, you can make the units work a little easier. 9.81 kilopascal per meter multiplied by, what's my static pressure? Oh, it's 30 kilopascal, isn't it? 30 kilopascal. Plus, what's my velocity or dynamic pressure? Well, we got to do a little doodling on the side to get the V, right? So V is equal to Q divided by the area. And it's 0.15 meter cubed per second divided by the area. Pi d squared 0.25 meters squared over 4. So the velocity comes in at 3.056 meters. And so now I'll put in the 1/2 rho 1,000 kilogram per meter cubed, 3.056 meters quantity squared. You could use the 800. It's 983, right? You can use that, but I mentioned I rounded off to 1,000 right up here. But yes, that's the better answer, to put in the 983 there. I should maybe have done that too. What's 9.81 times 0.983? Put that number right here. I don't have a calculator. Somebody have a calculator and read that number to me slowly. 9.81 times 0.983. 9.643. Okay, very good. There. So now we can put in 9.64 instead of 9.81. Okay. Now let's continue on. This I have to work on, but here I'm going to subtract off the saturation of 19.9 kilopascal. Okay, so I'm going to have kilogram meters per second squared. So a kilogram meter per second squared is a Newton. Then I divide by meter cubed. I'll get okay, it'll be a Newton meter divided by meter cubed will be a Pascal. And so what does this work out to be in pascals? What do you get for this number if you have a calculator?
4,590.
So 4.59 kilopascal. So you subtract 19, so you can see the importance. It's 30 plus 4.59 minus 19.9. All that gives us the kilopascal. Okay. So what do we get for the final answer? Then divided by 9.64. About 1.5 meter. Give me a thumbs up if you agree. 1 thumbs up, 2 thumbs up, 3, 4, 5. Good. So answer is A. Just have to remember the net positive suction head is the combination of the static plus the dynamic. That gives us the stagnation minus the vapor. Okay. The only possible dimensionless group that combines velocity, which is meters per second, length, which is meters, fluid density, oh, I forgot what density is, kilogram per meter cubed, and surface tension, oh boy, I forgot surface tension. What is surface tension? What let me do a little doodling on the side. Is that energy per unit area? Is that force per unit length? It is, force per unit length. So if I'm thinking SI, Newton per meter, and a Newton is a kilogram meter per second squared, divide by that meter, the meters cancel, I'm left with the funny unit of SI being kilogram per second squared. Now, some people will say, no, we don't want to work in the SI units. We want to work in the fundamental dimensions. Okay, fine. This would be length per unit time. This would be mass. No, that's not length. I mean, that's length, not mass. This, it would be mass per length cubed. And this one is mass per time squared. You know what? It's okay, I think, to work in dimensions. I also think it's okay to work in SI units. So let's just check them. Does this one work? So if I put length, that's a meter, then I'll have kilogram per meter cubed, then I'll have kilogram per second squared, and I'll have volume meter cubed. Will that work? No, it will not work. You have mass and mass on the numerator. So right away, anytime I see a rho times a sigma, it isn't going to work. But the rest of them have rho over sigma or sigma over rho, so that looks like they're going to work. Let's try this one. This is mass per length. Here, let's do it this way. Kilogram per meter cubed times meters per second times meters squared times kilogram per second squared. Will that work? The seconds are going to mess it up, right? No. Professor, it's a lot easier to guess. No, we don't want to guess. Let's keep working. Sigma, that's a kilogram per second squared. Length, meter, meters per second, but both of those are squared. And then the density is a kilogram per meter cubed. Is that going to work? Nope, not going to work. So let's try, I know that I messed this up. Let me make some room here. Density, kilogram per meter cubed, times length in meters, times velocity, meters squared per second squared, divided by sigma, which is kilogram per second squared. Will that work? There it is. Makes sense? All right, let's move on. For Stokes flow, the drag coefficient is proportional to the Reynolds number. The drag coefficient is inversely proportional to the Reynolds number. The drag coefficient is independent of the Reynolds number. The drag coefficient is a constant that depends on the Reynolds number, or is a constant that does not depend on the Reynolds number. You tell me. All right, well, what does it conjure up in your memory about Stokes flow? It's over a sphere. And so you think of a sphere, and you have this flow over a sphere. And what about the Stokes flow? Is it high Reynolds number, low Reynolds number? Very low Reynolds number. So it's low Reynolds number. It's so low that, do you have a large wake region? No, you don't have any wake region on the backside for Stokes flow. It's real low Reynolds number. It's creeping flow. What do you mean by creeping flow? Really just slow flow around it. And so the flow sort of separates, goes around the object, and rejoins on the back side. That's Stokes flow. Okay. Low Reynolds number flow. So maybe you think about the drag coefficient, C sub D, because that's what we're focusing on, the drag coefficient, and you think in your mind of that plot of the Reynolds number. And if I go with really low Reynolds number, slow flow, what did the plot look like for flow? It was something like this. Then it went kind of flat. Then it did a little dip with the golf balls dimpling and onset of turbulence before the separation point, etc. But we're focused on this region right here. What does it look like in this region right in here? Low Reynolds number. Looks like a straight line. This looks like a straight line. Okay. Is this, what type of scale do we have for C sub D and Reynolds number? Is this a log or linear? Log linear. It is log, and then the same thing down here. Log linear, it's log. It's a log plot. What gives you a straight line on a log plot? Just like this class, after I finished the final, don't ask me a question about fluids. I did the same thing in every one of my math classes. Right? Don't ask me a thing about a function or derivative or an integral or anything. I don't want to think about it. I passed that class and I'm done with it. So if you have a function, let's say y is equal to a over x, and I take the log of both sides, what do I pick up? I pick up the log of a, okay, log of a, or just another a, minus the log of x. What's that coefficient? It's negative right there. It gives me the downward slope. So it basically, C sub D is a constant divided by, C-O-N-S-T, divided by the Reynolds number. That's the characteristic. How about if I go back and I look at the friction factor as a function of Reynolds number in the laminar region? Hey, that was a log plot. The friction factor was a straight line coming down. What was, hey, you mean the friction factor is some constant divided by the Reynolds number on the Moody diagram in the laminar region? What was the magnitude of that constant for the flow in a pipe, laminar region, blah, 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 Moody diagram? What is that? 64. There's too many numbers to remember. I got 2,300, I got 500,000, I got 64. What about here for the Stokes flow? What is this constant right here? I know this is a tricky one. It's 24. You can derive it and develop it, but it's 24 for Stokes flow. So, armed with that information, which is your best answer? Maybe I should have said proportional to the inverse of the Reynolds number. Isn't it proportional to the inverse of the Reynolds number? This one, D, I know some people said, hey, I think it's D. This is kind of an oxymoron. It's like, what? It's a constant that depends on the Reynolds number. Like 5 is equal to a function of the Reynolds number. What? No, that doesn't make any sense. That doesn't make no sense. All right, we're done with that one. Manometer, I'm not going to solve another manometer problem. You have to be able to solve them. Dimensional analysis problem. This was out of, what, chapter 7 or something? A stir is used to mix chemicals in a large tank, develop a dimensionless relationship for the shaft power. This is what is kind of my intended primary output as a function of the stirrer diameter. So we're interested in this stirrer diameter. The tank diameter, the liquid density, the liquid viscosity, the angular velocity or speed of the stir, and the depth of the fluid. So those are all my parameters. So what do we do is you want this general relationship, so you just put out, I would put the first one is what is going to be my, let's say, my response or my output, and then I would list the other ones, maybe in the order that they give them. D, L, rho, mu, omega, let me put omega a little better there, and then H. True? And I would count them up. You can't make an error here. How many do I have? 1, 2, 3, 4, 5, 6, 7 parameters. Then I have to put them in dimensionless or fundamental form, not dimensionless form. What is my fundamental dimensions for each of these parameters? I'm going to just work in the fundamental SI unit for those. So what about the power? Power. Well, you would maybe say, doodle on the side, kilowatts. Forget the kilo. It's a watt. It's a joule per second. A joule, Newton meter per second. What's a Newton? Kilogram meter per second squared times my meter over second. Looks like I finally have it down there, don't I? Is it my kilogram meter squared per second cubed? Is that true? Then D, meters, length, meters, density, kilogram per meter cubed. Viscosity was a kilogram per meter second. What's my omega? That's a bad looking omega. Come on, do a better omega. What is my omega? Radians per second. So is that meters per second? No, it's just, we talked about that. What's a radian? A length over length. It's dimensionless. The measure of angle, length over length, radian is dimensionless. So it's just 1 over second. Then H, meters. So we count up the number of primary dimensions. They're almost always 3. Then how many pi groups? 4. So we're looking for 4 pi groups. And so what you do is you pick the ones you're going to build around, or in other words, you pick ones that you're going to use repeatedly in the other ones. So let's do this. Let's build around W dot. All right. And then what else do you want to build around? Mu, because you know you're going to get something like a Reynolds number. So now I need 2 others to build around. Which one would you like to build around? D. You can build around D. And last? Which one? Height. There you go. These are the most important. And I just see that you're just going to have to pick some other ones. So let's do a pi group, the first pi group, which is W dot. And I like to write it out like this. I know it's probably unorthodox underneath kilogram meter cubed per second cubed. If I start multiplying and dividing, and I can only use this one, and this one. So if I need to get rid of the kilogram, what do I have to do? I have to take in the divide by rho. That'll get the kilogram per meter cubed. Won't that get rid of the kilogram? Say goodbye to kilogram and don't introduce anything with the kilogram again in that pi group. All right. Now let's get rid of the next hardest one, probably seconds. So if I want to get rid of second cubed down there, then I will divide by omega cubed. That will give me seconds cubed. Say goodbye to the second cubed. Now I only have length to the 6th power. Okay, what do I want to use? Well, I've used this one, omega, and I used rho. I can only use L. So I'll divide by L to the 6, and that'll give me meters to the 6. And voila, I checked it. And so my first pi group is just like that. Let me clean it up just a little bit. So it's going to be W dot divided by rho omega cubed d to the 6th. No, that's not 6, is it? What did I mess up on? Yeah, this is a meter squared right there. That's a squared, then that's the 5th. Sorry about that. So there you go. That gives me the 5th, and then that cancels it. Okay? All right, let's go for the next pi group. The most complicated is mu. And mu, I work out units below, kilogram per meter second. Let's get rid of the kilogram by dividing by density. If I divide by density, then I have kilogram per meter cubed. The kilograms are gone. And I have meters squared. Okay, let's get rid of the second. So I'll divide by omega. So that'll give 1 over, well, there. Then that'll get rid of that second. Now I have meters squared. And so I'll divide by L squared. That'll be meters squared. That'll work. So my second pi group, to clean it up, is mu over rho omega L squared. That looks like the inverse of a Reynolds number. I anticipated that. The other pi groups, pi 3 is easy. D divided by L. And the fourth pi group is H divided by L. And so I would write it, the general relationship as W dot divided by rho omega cubed L to the 5th is a function of, and we don't know what that function looks like, but it's a function of, I'm going to put it like this, rho omega L squared over mu, looks like a Reynolds number. I'll have D over L, and I'll have H over L. That's my general equation. My dimensionless relationship. Leave this dimensionless on this side. And each one of those are dimensionless groups. I wanted to cover more material. Thank you very much for your attention. I'm out of time. We'll see you 7:30 a.m. Thursday. Yes, sir.
Can you kind of run through the questions really quick so we can pause them like on the video and maybe work it out?
So this is a car traveling problem I was going to solve. This is oil flowing problem. I don't have the answers on here though, just the problems. This is a ventilation problem. This one was a longer problem. Basically do Bernoulli's. I think I tried to set it up like this last time. This is a much simpler problem, calculation of the maximum production power, hydrodynamic dam. This is a pump problem, doing getting the net, the maximum flow rate to avoid cavitation. On this one, you have the curve for the net positive suction head required goes like this. And then you'll have a curve for the net positive suction head available. And when the available goes below the required, you have cavitation problems. And at this point, that's your maximum Q to avoid cavitation. I think we solved the problem like this before. You have an aircraft and you're doing lift. You change the weight of the aircraft. It changes the speed at which it takes off. This is a problem like this. You should be able to work examples out of the textbook, which require you to go back and start from the governing differential equation for incompressible Newtonian fluid in a cylindrical coordinate system, go back and get a differential equation and solve analytically for that velocity profile using the two boundary conditions at the wall and at the center line. I've done it in class, I know I have. But it's important to do that. And it's worked out in an example in the textbook. And this is a siphoning problem. I don't like the units because it's not going to be in those units on your exam. If I give you a problem, it'll all be in SI. But it's still a siphoning problem. You use a modified Bernoulli. And the last is another dimensional analysis where I have these V's and L's and D's. Did that help? Thank you.